Oxygen depletion in surface water is a major impact of uncontrolled emissions of organically polluted wastewater. Sewage treatment plants are designed to eliminate oxygen-demanding pollutants. But what is the natural attenuation capacity to deal with organic pollutants when no sewage treatment plants are present? In this lecture we will discuss oxygen depletion and reaeration in natural water bodies as a result of sewage emissions. As discussed in previous lectures, discharge of organic pollutants in surface water reduces the dissolved oxygen concentration. This might possibly lead to oxygen depletion and die-off of oxygen-dependent aqueous life forms like these fish. When is a drop in dissolved oxygen concentration detrimental? Is the dissolved oxygen concentration automatically restored? In the aeration tanks of activated sludge systems, we mechanically replenish oxygen by air compression and bubble aeration, similar to the aeration techniques in drinking water treatment. In nature, we are dependent on passive or diffusive oxygen transport. Under equilibrium conditions, the dissolved oxygen concentration in surface water is determined by the air oxygen concentration, the air pressure, the water temperature, and the oxygen consumption rate in the water body. The liquid solubility of a gaseous compound is gas-specific and is determined by Henry's law. In this graph, the oxygen solubility is plotted by the red dotted line as a function of the water temperature, assuming an atmospheric oxygen partial pressure of 21 kPa and a total air pressure of 101 kPa. Other lines represent the liquid oxygen concentration versus temperature at lower oxygen saturation percentages. When an organic pollutant expressed in BOD enters the surface water, bacteria starts to oxidize the pollutant, using the liquid dissolved oxygen as an electron acceptor. As a result, the oxygen concentration drops. Fish will die off when the concentration drops to below 4 to 5 mg per liter. The non-biodegradable carbon sediments to the bottom and the biochemically oxidizable carbon will be transformed to carbon dioxide. This CO2 is subsequently used by macrophytes or algae for growth, while producing oxygen, which again raises the water oxygen concentration. The difference between the maximum oxygen solubility and the actual concentration is called the oxygen deficit. When such deficit occurs, also a net flux of oxygen from the air to the liquid will start via passive diffusion following Fick's law. This physical reaeration process is generally much more important than biological oxygen production. The degree of oxygen deficiency determines the oxygen transfer rate. Since oxygen deficiency is determined by the maximum oxygen solubility, the water temperature has a distinct impact on the oxygen transfer rate. In addition to temperature, also the salinity level has some impact as it determines the maximum solubility as well, though to a much lesser extent. Next to the maximum solubility, the mass transfer coefficient or reaeration coefficient, K2, governs the oxygen flux. The value of K2 depends on temperature, liquid surface to volume ratio, water turbulence and the liquid flow velocity. Therefore, the K2 value drastically differs between stagnant lakes and fast-flowing rivers as indicated by the K2 values in this table. The drop in the dissolved oxygen concentration as a result of BOD emissions, followed by the liquid reaeration, is described by the so-called oxygen sag curve. On day 1 of this example, the BOD concentration in the water suddenly increases to 50 mg per liter. Owing to bioconversion, the BOD concentration exponentially drops until all BOD is converted. Since this bioconversion requires oxygen, the oxygen concentration rapidly drops at day 1, creating an oxygen deficiency. This deficiency invokes the physical reaeration process. The oxygen consumption rate and simultaneous reaeration process, or oxygen sag curve, is described by the Streeter-Phelps kinetic equation. In this combined biological-physical equation, the Kd, or biodegradation rate, and the Kr, or reaeration rate, fully determine the shape of the curve. Now imagine a sudden BOD increase to 15 milligrams per liter in water with a maximum dissolved oxygen concentration of 10 milligrams per liter. Assuming a Kd of 0.6 per day and a Kr of 0.4 per day, the oxygen concentration drops to a minimum of about 3 milligrams per liter after 2 to 2.5 days. Now, what happens when with the shape of the curve when we lower the Kd value, keeping the Kr at the same level? Indeed, the drop in oxygen is less severe, but the impact of the pollutant is longer present. Finally, let's have a look to what happens when the Kr drops. For instance, when the river becomes more stagnant by a low flow. Let's put the Kd back to 0.6 per day and set the Kr to 0.15 per day. Now, the BOD dosage has a much more severe effect on the water oxygen concentration, and it takes also much longer before the equilibrium is restored. Also, an increase in the BOD dosage will lead to a more severe drop in the oxygen concentration, possibly leading to complete anaerobic conditions. Enhanced bioconversion and enhanced oxygen transfer are the prime principles of activated sludge system for sewage treatment. In fact, in these engineered mechanized systems, the natural processes of organic matter mineralization and oxygen equilibrium restoration are optimized. When limited funds for engineered treatment systems are available, nature can be mimicked in non-mechanized land-based treatment systems, called lagoons or pond systems. In the pond systems, all before-mentioned processes take place. As such, pond systems are also optimized for enhanced bioconversion and enhanced oxygen transfer. The downside of a pond system is that it occupies large areas of land. Since land is extremely expensive in or nearby cities, large and expensive conveyance systems are required, like in this 200-hectare example in Amman, in Jordan. In such case, several tens of millions of euros are spent only for sewage transport. In a treatment pond, a similar symbiosis occurs between the bacteria converting BOD and algae consuming the CO2 and the mineralized nutrients. In the meantime, the algae or macrophytes produce the oxygen required for BOD conversion. Since solar light is required for the photosynthesis of algae, pond systems are characterized by large surface area filled with shallow water. The large surface area also facilitates the physical mass transfer or diffusion of oxygen from the air to the liquid. Obviously, in pond systems, biomass concentration and thus bioconversion rates are much higher than in natural ecosystems. Therefore, pond systems are classified as land-based wastewater treatment systems. With more concentrated sewage, the degree of engineering increases. The high suspended solids concentrations are largely scavenged by a more deep anaerobic pond. In this pond, the organic matter is stabilized under anaerobic conditions. The anaerobic pond is then followed by a less deep facultative pond with only low dissolved oxygen concentrations. Finally, the shallow maturation pond will remove the final pollutants and will restore the oxygen concentration to the required level. Since the solids accumulate in the anaerobic pond, solids removal should be part of the standard operation procedure of the pond systems. However, in by far most cases, solids are not removed, eventually impacting the liquid flow regime and thus reducing the pond capacity. The exact design criteria of such pond system goes beyond the purpose of our lecture series. Temperature, wind, solar radiation, liquid flow regime all impact the biological reaeration and physical reaeration coefficients that are important design criteria for pond systems. And generally, exact values of these coefficients are not known. In many cases, pond systems cannot cope with the increasing load of pollutants. If the natural oxygenation capacity is insufficient, such pond systems might be equipped with mechanical surface aerators. This system almost looks like an activated sludge treatment plant, right? One can question if in such conditions we should proceed with pond systems. In much more compact treatment system, system control is also much easier. Space availability, investments, operational costs are important factors determining the choice of the responsible agencies in such situations. In the next lectures we will further concentrate on the mechanized compact treatment systems such as those operational for sewage treatment in the Netherlands. So please hang on, don't forget to have a look to the questions and the answers of this course.